Okay. Good afternoon. We are a little early for once on schedule, but given that we are a full house and unfortunately we cannot let anyone else in and all our speakers are with us, we thought we'd take full advantage of the extra time and start a few minutes early. So welcome, my name is Letizia Rossano. I'm the director of the Asia Pacific Center for the Disaster Information Management. It's a regional institution of ESCAP, the Economic and Social Commission for Asia and the Pacific. And I'm very pleased to welcome you all to this interactive session on artificial intelligence and its application to disaster risk reduction. And I'm joined by an esteemed panel of experts and a colleague who is co-moderating with me, Lorenzo. I'll let you introduce yourself.
Thank you, Letizia. Good afternoon, everyone. It's a pleasure to have you here. My name is Lorenzo Nava. I'm a researcher at the University of Padova in Italy, very close to Venice, but unfortunately it's nothing alike. My research is about artificial intelligence for landslides investigation. Specifically, I use it to improve landslide predictions, but also disaster response. And for the last 3 years, I contributed to the work of the ITU WMO UNEP focus group on AI for natural disaster management. The focus group was tasked with laying the groundwork for standards, but also capacity building. And for the working group of educational material, I was the chair. Currently, the focus group is transitioning, so we are becoming a global initiative, and the kickoff will be on the 6th of November in Barcelona, if you want to come. The global initiative will be built on the outcomes of the focus group as part of this technical part of the Learning Lab. So I'm very excited for this session. Thank you all for coming, and back to you, Letizia.
And it is my pleasure to invite our opening speaker and for the opening remarks, Dr. Joel Joseph Marciano is the first anchor and director general of the Philippine Space Agency and the presidential advisor on space matters. Dr. Marciano is also a full professor of electrical and electronics engineering at the University of the Philippines, is the recipient of several recognitions for his research, teaching, and public service. And in January 2023, he was conferred an honorary doctorate by Hokkaido University for distinguished contributions to advancing education and research via international exchanges. So Dr. Marciano, thank you so much for being with us. It's our pleasure.
Thank you. I will go and take this.
Please.
All right. So Letizia Rossano, Director of the Asian Pacific Center on the Development of Disaster Information Management. Dr. Lorenzo Nava over there from the University of Padua. Excellencies, esteemed speakers and delegates, participants from academia, government, private sector industry, civil society organizations from here and abroad. Ladies and gentlemen, as we say in the Philippines, magandang hapon po, good afternoon to all of you. You probably were not expecting slides for this opening message, but I did prepare a few, so please bear with me. And thank you for the privilege of delivering this message at this Learning Lab event, AI Innovations in Disaster Risk Reduction Management, Enhancing Systemic Risk Analysis for a Resilient Future. We're here today, I believe, bound by a common purpose to build resilience, reduce disaster risk, and ensure sustainable, safe futures for all, cognizant of the need to understand and leverage tools and implements such as AI for good. My message this afternoon starts with Yamang Kalawakan. It's a Filipino portmanteau we invented, which translates literally to space wealth. We use it, however, in the figurative sense to refer to the collective resources, people, infrastructure, capabilities such as AI, the institutions, policies, and environment. In other words, the emergent domestic space ecosystem in the country that enable the Philippines to contribute and benefit from scientific and economic developments in this field. So a hearty welcome to all of you. Let me now proceed. There we go. A hearty welcome to the Philippines to all of you, where There are over 2 million square kilometers of maritime waters encompassing an important part of the so-called coral triangle. Thousands of species of coral, many of which have well-established commercial value. Millions of species of flora serve as vital natural ingredients in many commercial products, and many species unique to the islands. So it's a mega diverse country. That's probably one way to describe ourselves, who and what we are, among various other perhaps more profound ways. But where we are, though, is right over there, where the green arrow is pointed at. And you probably heard it this morning. The president said we're in the Pacific Ring of Fire in the Pacific Typhoon Belt. Now, this archipelago of over 7,600 islands populated by over 110 million people showcases diverse ecosystems, each facing unique vulnerabilities to a range of natural hazards. These incessant challenges underscore the need to mobilize all available and new resources, tools, and implements strategies, including artificial intelligence, for enhancing the capacity to reduce and manage disaster risk. So thus, space beckons, particularly with its high and strategic vantage point. It beckons to us, or rather maybe we look up to space. The space agency in the Philippines is PhilSA, established just over 5 years ago through a Republic Act, the Philippine Space Act, is contributing to these efforts. It's the central government agency addressing national issues and activities in space, science, and technology applications. So we operate under the office of the President to ensure alignment in national policies and priorities. The Philippine Space Policy outlines 6 key development areas for space development: national security and development, space R&D, space education and awareness, space industry capacity building, international cooperation, and certainly hazard management and climate studies. So we harness space-based technology for more effective monitoring, prediction, and prevention of and response to natural disasters. A space agency brings new and additional tools to the tables of decision-making, policy formulation, and governance. And so in line with the Philippine Space Agency, Philippine Space Policy, our vision that is of a nation bridged, uplifted, and empowered through the peaceful uses of outer space, and our mission of promoting and sustaining a robust Philippine space ecosystem that adds and creates value in space for and from Filipinos and for the world. Now, in driving socioeconomic value from and benefit from investments in space capabilities, both upstream and downstream, we look at this space data value chain. Serving as a strategic framework, we look at each block to address gaps, identify opportunities, and guide partnerships and cooperation that help build commensurate strength in each component. So first, you start with the satellites and upstream infrastructure, and then you ask yourselves, do you have access to this data and services from the satellites? Are they suitable for you? The next thing you ask is, do you have infrastructure to download and host this data? In other words, bring the services to the ground, to the planet Earth. And once they're on the ground, you ask yourself, do you have capacity to analyze and interrogate this data from which you derive insights? And subsequently, the valley of death. Is there impetus and resources to act on these insights? And if there is, and you follow through on that, then we can all realize some socioeconomic benefit and value from such investments. So where does AI come in here? Where is AI here? Well, it's there. Increasingly able to enhance our capacity to analyze data and generate timely insights, helping us in generating greater impetus as a consequence, leading to greater impetus more than before to act on these insights. And so last year, we produced a total of almost 31,000 maps, the space agency, many of which support environmental monitoring and DRRM operations. So beyond the realm of R&D, these are now being translated into operations and into services. Among the maps showcased here are those for oil spill monitoring, monitoring of burnt areas, mapping, estimating damages, agricultural drought assessment, and also landslide delineation. And we recognize the significant role of AI in enhancing space technology capabilities for DRRM. While satellites provide vast amounts of data, including near real-time imagery and climate patterns, AI amplifies the utility of this data. By applying these algorithms to satellite images, we can rapidly process and analyze complex information, identifying patterns and risks that might otherwise go unnoticed. So flood extent maps are one example of these operational products that are churned out hours, mere hours after a flooding event in the Philippines. So this is generated from models developed over 7 months by a team in the space agency. This investment in time and effort pays off in terms of significantly reducing the amount of latency for releasing the information to concerned agencies and even to the public. So flood extent maps are being routinely produced using this AI model, enhancing our ability to respond to and manage flood events effectively. See some numbers there. Another example is this 2023 National Mangrove Map, launched in collaboration with the Department of Environment and Natural Resources, the DNR, this August. You will find a copy of this map in the National Museum, right? Kind of a artwork as a result of the work of science. It's quite interesting, but you'll also find it in the dashboard in electronic form. Mangroves serve as natural barriers, playing a critical role in disaster mitigation by protecting coastal communities from storms, floods, and coastal erosion. Given their importance, continuous monitoring and protection of these ecosystems are essential to ensure their ongoing contributions to reducing risks from disasters. Mapping these resources is crucial to monitoring their health, the loss, and restoration efforts. This map was made possible through the fusion of satellite imagery, ground validation and mobilization, open data, satellite images, and AI. Now, the map, you see there the points that have been validated so far on the map. Once the data, satellite images was encoded into the algorithm, the National Mangrove Map could be was generated rather in just 48 hours. Without AI, the same process would have taken roughly a year. This achievement was made possible by 2 people in the agency who spearheaded this effort. With the AI-powered model, what once required a team can now be accomplished by just 1 person. The end result, the AI-generated mangrove map, has an accuracy rate of about 90.72%. And this highlights the hard work and dedication of the team, but also demonstrates the transformative potential of AI in advancing our environmental monitoring capabilities. Quite important is the ability with AI has also allowed us to be more agile and engage local communities in taking action on the maps, particularly in the ground validation loop. Now, knowing fully well that the AI was going to make mistakes on the map because of the model is not perfectly trained and you need a lot of data to train that model, counterintuitively, we still released it to the public with the mistakes and all, but not without the challenge and the invitation to validate the map precisely. So as promoting citizen science and volunteerism in taking these maps and promotes a sense of ownership in the communities and environmental custodianship of the mangroves that are in their backyards or in their communities. So the video that you see here shows, it was playing, or maybe it was playing a while ago, shows the ground validation campaign using aerial drones and a mobile phone application that ordinary people use, taking pictures of the mangroves, telling us where we got it right, or where the algorithm got it right and where it got it wrong. And this data was fed back to refine the model. So this community engagement, as mentioned, fosters not only great appreciation of the space capabilities, but a better sense of ownership and custodianship of the natural environment. Now, our ultimate goal is always to derive socioeconomic benefit from these activities. This can only be achieved if the information from space data and maps are acted on. And one compelling example is highlighted in this slide where credit goes to the DNR and law enforcement agencies who took the satellite images and information on the ground and shut down an illegal mining operation as a result. And of course, the Office of Civil Defense, when we see them posting images of how they're using the maps generated by the space agency, in this case, a deadly landslide in Davao de Oro, where the value adding was done on the landslide image by overlaying maps, overlaying the footprints of the buildings that used to stand there. So to an emergency responder in the field, you stand in the middle of the rubble and you say, I don't recognize the place, but according to this map, there was a house here. So maybe we should try to focus our efforts first here. And so, yeah, AI and disaster risk reduction and environmental protection is quite crucial capability, and especially when dealing with mandates, as is the default with our experience with government agencies in this country, collaboration becomes even more crucial in acting on the data. And so to close this opening remarks, I would like to, first of all, before I play this video, it's a short video, I would like to express my gratitude to organizers of this forum, to UNESCAP, APDIM, ITU, HHI, and the University of Padua for this opportunity. I also invite you later on this afternoon to another partner event in meeting room 2 and 3, just across the hall, featuring strengthening ASEAN disaster risk management by harnessing Copernicus data. As we explore the confluence of AI, space technology, and DRRM, let us all reaffirm our commitment to supporting one another. We are reminded that the challenges we face are shared. The impacts of disasters and climate change are borderless and felt across a swath of communities, no matter how remote or developed. However, gathering here today also allows us an opportunity to continue to find collective solutions by learning from one another's experiences and by fostering partnerships that can amplify our individual strength and resilience. Finally, the integration of AI empowers us to enhance our preparedness and response capabilities, making our communities more resilient in the face of adversity. Through collaboration and shared knowledge, let's all build a robust framework that not only mitigates disaster risk, but also fosters a culture of innovation and proactive action. And so I will play this video in closing. Thank you very much. Mabuhay po kayo lahat.
Thank you so much, Dr. Marciano, for your keynote speech. So helpful and interesting in really setting the tone and giving us an overview of how you're doing things in the Philippines, but a lot of these problems and issues are really shared by all countries. As we start to dive into the more technical aspects of the session, I just want to make sure that all the newcomers have also downloaded the link that was on the table so that they can participate interactively in the discussions. And I also take the opportunity to remind ourselves that this is a joint session organized by ESCAP, but also the International Telecommunication Union, ITU, Fraunhofer Institute for Telecommunication at the Arts Institute and the University of Padua. So it really is a joint effort, like most things we should be doing in this field. And with that, I hope you downloaded the app or the link rather. Lorenzo, we're getting to know each other a little bit and using, why don't you run us through this?
Yeah, sure. Thank you very much, Letizia. So if you can join Mentimeter through the QR code that were on your table, but also by writing menti.com and then inserting the code. So now we are going to ask you some questions just to get to know you, as Letizia said. Okay, perfect. You already started to. Okay, very nice. Philippines, South Korea, Australia, Singapore. Wow.
Nice contingent from the region and beyond.
Yeah, very nice.
It's
okay.
Good. Yeah, go ahead.
Okay, and then...
So we're asking you, what is your role in disaster risk reduction? I think we have some responses just to get a sense who's in the audience. Policy, data analyst, policy making, interesting research, urban planning. So I think we have a nice coming up, a nice key issues. On the one hand, the policy, on the other one, the data experts. So I'm very glad that we got both of you in both sets of fields in the room. Monitoring, response, very good.
Really variegated.
Yes,
very nice.
Yes.
Okay.
We go on to the next one. What is your sector? Government, academia, private sector, other. There you go, in real time. Government is by far the largest sector represented. Academia is nicely present. Private sector is more than academia at the moment. And I wonder what the other is.
Yeah, I saw a lot of research before.
Yes, indeed.
Okay.
And I think we're done with the slides on the getting to know each other. Oh, no. Do you use AI in your DRR work? Yes or no? Okay, if we had like 50 responders before, we can't have 6 now. Even I can figure that math out. Feel free to say no if you don't. It's totally cool to say no. It's totally fine.
Yeah, it's anonymous. So.
Sorry, there was, I think, an uploading issue. Maybe we can go back to the previous slide. I think there was an uploading issue with the data. Okay. All right, this is more telling. 37 to 43. Very good. Okay.
Last one. For what purpose, if you do use it?
Is there a...
Probably... Oh, no, okay. It's starting.
We left it open, so it's completely open. As I said, we might use some of the anonymous answers just for research purposes, but it's just feel completely free. This is a judgment-free area, and it's an interactive moment of discussion with each other. So don't It's very interesting to see that it comes to specific hazards.
Mapping, monitoring.
Exactly. Hazard analysis, data analysis, reporting, proposal writing, preparedness.
ChatGPT is...
I used to work in resource mobilization. That caught my eye. That caught my eye. All right. All right, so now we got a sense.
Okay.
And
yeah, so thank you for being so interactive. We got a lot of answers. I'm very excited for this part. This is an extract from the outcomes of the focus group. And we extracted 4 key concepts that we believe are very important for AI, but of course there are many more, and if you want to know more, just get in touch. I will be more than happy to discuss with you. And I will describe how we structure this part of the learning lab. So we'll have 4 blocks, which will be associated with these key concepts. And these key concepts are data annotation, data bias, then we have model evaluation and transparency, and at the end we will have the human-centric design. How this is structured is that we will ask you first, what's your definition of these concepts or your understanding of it, and it's not a problem if you don't know what is it, just try your best guess. And after that, our speakers will present their use cases, and these use cases will be related to the concept. And then after the speakers, we will give you our definition, the definition of that we define in the focus group. And I would like to underline that how we came up with the definition was through literature review, engagement with experts, but also the analysis of 27 curated use cases. So without taking any more time to the blocks, I think we can start with the data annotation. So it's your turn to give us your definition of data annotation related to AI in natural disaster management, please.
data storytelling, reference data to source, tagging data, identifying objects, keep them coming.
Yeah, many.
Data classification, labeling and tagging. Label comes a few times. Providing labels on data, metadata, sense making. Okay.
Yeah, I think, yes, there is more on this page that we
It's
can't.
scrolling, maybe we need to scroll or
Okay.
we'll go to the next one. Okay, that's good. It's good sense, good sense. Thank you. Thank you for the inputs.
And so is data annotation relevant for your work or not?
Okay.
Yes, that's good. That's good. There are no no's, so it's great.
Okay. Shall I go to that? Okay, yes. We have now Noel Jerome Borlogan, Senior Science Research Specialist at the Philippine Space Agency, who is going to talk to us about data annotation. Go ahead.
I'll stand there on the side so that I won't block the screen. So, good afternoon, everyone. Once again, I am Engineer Noel Jerome Borlogan, here to present to you one of our use cases of using artificial intelligence in our line of work at the Philippine Space Agency. So my topic will be flood extent mapping in the Philippines using AI. I'll jump right to my presentation. Where should I click this? Can you proceed to the next slide? I'll just maybe mention it to next slide since it's working. All right, it's working now. So as a bit of introduction, here is a global data of the natural disasters occurring in our world from 1970 to 2024. So according to these records, although this is not all of the occurrence, these are just the events that were recorded by the organization. So according to this, flooding and extreme weather events are the most disasters that occurs in our lives. So these are also the two these are the two disaster events which also cause the most damage in our countries and in our nation. So it really calls for a method for fast and reliable mapping algorithm for flooding extent so that we can use the flood maps for disaster response and for informed decision making, especially in the Philippines where we are struck by an average of around 20 typhoons and around 5 to 10 of which are destructive. So we at the Philippine Space Agency decided to create an algorithm using artificial intelligence to be able to create such maps in a quick and timely manner. So the data set that we used is Sentinel-1. Sentinel-1 is a polar orbiting all-weather day and night radar imaging mission for land and ocean services. So this is not the only data set that we use, but this is the one that we developed a model on because Sentinel-1 is a regular data. It has a revisit time of around 12 days. And also, this has a nationwide coverage. So taking advantage of that, we are able to predict when this data set will come, and that's so that we can also generate maps when these images are available for us. So one of the satellites was actually decommissioned in 2016, but another satellite, the Sentinel-1C, will be launched soon by the European Space Agency. So here is a quick overview of our process. We used Sentinel-1 data. We used one post-disaster, and we also used two pre-disaster images. We downloaded data from the Copernicus Data Space Ecosystem. The processing time is around 4 to 6 hours from data access. And we used open source software, QGIS, Snap, and Python. We processed them in our high-performance computers. Here is a quick workflow of the whole process. So from the three images, one post-disaster and two pre-disaster, we applied the normal SAR workflow for processing SAR images. We apply orbit file, we calibrated it to beta-NAT, multi-looking, terrain flattening, gamma-NAT, co-registration, and we pre-processed the SAR image. From the pre-processed SAR image, we then feed it to an AI model. So the AI model will generate an output identifying the flooded extents from the pre-processed SAR image. And then we just post-process it to clean up some of the areas which are actually not flooded, but due to the some errors in the image. And then from them, we generate shapefiles and map layouts which we distribute to our social media pages and to other national government agencies. So here is an example of the image that will be generated out of the pre-processing. So we visualize this in QGIS using a RGB color composite combination. The post-typhoon image will be assigned to the red band, and the two pre-typhoon images will be assigned to the green and blue bands rather. the picture on the right shows what it looks like for an example of an preprocessed star image. So if you can see, there are cyan areas in the image, cyan or bluish or light bluish, sky bluish spots in the image. Those are actually the areas that are potential flooding due to our algorithm, because using SAR actually has a low backscatter in the red band, because the water has a specular reflection property which makes a SAR image having low backscatter values. And so the blue band and the green band demonstrates areas which are not flooded. Therefore, when we combine those three images in a composite, it should appear in the preprocessed image having a cyan color. Let me try. Here in the color palette here, we can see the combination of blue and green will generate a cyan color. Meaning, these are the ones with high backscatter values, because those indicates not flooded areas. And then, because of a low presence of red, that's why here in the color combination, we see here the cyan colored areas. That's how we identify flood from the preprocessed star images. So now, again, this is an example of a preprocessed star image. As you can see here, you can see the cyan areas which are potential or possible flooding in this area. So how do we use AI in that? We use AI in order to isolate the flooded areas from the preprocessed Sentinel images, because as you can see in the image, there are many actually cyan colored areas. There are many different levels of cyan, especially when using satellite image bands, whose bands have a floating point values, meaning it's decimal, so it can be from negative 12.5, negative 11.7, it can vary. And we are using 3 bands, so sometimes just a small change in value already, it can cause a change in color. For example, here, these are all considered cyan levels, and sometimes the difference from one cyan color to another cyan color can be just a small difference in some of the bands. For example, this can be high in green and blue, while this one retaining the same level of red value. It can appear like this just because there is a different value for the green and blue, and the possibilities are endless. So in training the AI model for flooding, it is very important to select the pixels in images which identify floods using the cyan colored areas. As you can see, maybe here in the next example, these are scenarios or areas which are flooded, and you can see the different cyan colored areas. So sometimes some of them, they are clear cyan, some of them actually appears greenish, some of them actually appears purplish. So there are many different pixels or combinations of values which can result into a cyan looking pixel. The challenge is identifying the proper pixels for flooding, because if we train the model with the wrong pixels, then of course our AI model will predict wrong flooded areas. And if we feed the AI with some of the pixels which are confusing, and then of course the AI model will generate maps which are less accurate. So from here, using AI, we generate something like this. This is actually identified flooded extents from the SAR image. Normally, what people do is that they identify thresholds for flooding, meaning they try to find a range of values which can satisfy or which can appear flooding to them. So what we did is that we generate an AI model so that we do not have to choose the right values or the proper values for the floods, because it takes time. Sometimes the threshold values is not consistent. Sometimes it's -11, sometimes it's -13. So in order for us to reduce that complexity, that's why we developed an AI model for identifying the flooded extents. And we simply apply post-processing to them so that we can clean up the data by applying different masks. We vectorize them, we filter by area, we add attributes, and then we generate the KML and the maps. So here are sample maps that we generated using Sentinel-1. So you can see the red spots, the red areas, those are the identified flooded areas. So these are maps which are generated regularly by our agency in order for us to be able to contribute to the disaster risk reduction activities as part of the national space program through the Philippine Space Agency. We post this in our social media pages, and we also distribute this through emails so that the concerned local agencies and national government agencies can be aware of the actual flooding incident in their respective regions. So I think that's my presentation. Thank you.
Thank you very much, Noel, for your presentation. This is a great application of automated mapping of flood. Thank you very much. Could we please go back to Mentimeter on my laptop, please? Thank you. In the meantime, if I can ask you a question, I would like to know if there is any opportunity for data annotation to improve the prediction of such model.
Right, of course. Right now, we do not claim that the flood model that we have generated is perfect already. So we are expecting some of the predictions to be misclassified in some areas. So data annotation can play a huge role in validating our model. And I hope that maybe the people who can see our maps can help us in validating the maps. So earlier, our Director General mentioned using citizen science or asking help basically from the general public to tell us whether the model that we have generated is accurate or not, or if it is correct or not. So through that, then if people can help us identify where the areas the flood model is getting a hard time predicting it right, then we can train our model again through the data set that will be provided to us.
Okay, thank you very much, Noel.
Sure.
So now is the time for give you our definition, which is that data annotation or data labeling, some of you wrote data labeling, is the process of assigning one or more class labels from a predefined set of labels to a given data object. Okay, this is from the report, exactly how it is. And I invite you to scan this code to access the website of the focus group, where you can find all these resources and also other very resourceful informations. And now is the time to move to the next concept, which is the data bias. And of course, like before, we would like you to give us a definition of what for you is meant by data bias. So please. Limiting data sets, assumption, data gap. My perception is, is my reality. It's true, indeed. Yeah.
Interesting feedback coming through. Okay. Shall I? Yes, thank you for this initial insights. And there's another one.
If it's relevant for you, data bias, at this point. No. One no at this time. Yeah, it's good. But yes is still ahead, so very nice.
Okay, so we're pleased to introduce you the next speaker for this morning, who's going to talk to us about data bias using the example of AI for operational weather forecasting. Ellen Marie Coy from the Deputy Chief and International Meteorologist and the UK Met Office is going to share her experience with us. So Helen, the floor is yours.
Thank you. So first of all, just thank you to the panel and fellow speakers for allowing us to be part of this session. I will say up front, I don't claim to be an expert in this at all. It is a field that is obviously still very rapidly emerging across all sectors, but that includes kind of operational weather forecasting. So just thanks to my Met Office colleagues, so our Chief AI Officer, Christine Dale, and then our Principal Operational Meteorologist that is working in the AI space, so Steve Ramsdale. So just thanks to them for their conversations and contributions to this to allow me to present some of that work today. So I think this is something really, it fits against anything, okay? So obviously we're against this revolution in artificial intelligence, and it has this potential to completely fundamentally change the way we work and live and operate in some of these industries. And weather forecasting is no exception to that. And that's really the data biases and so on that I'll talk about in this regard. But just to show of hands, any other operational forecasters here? Okay, so some, okay, but the vast majority, I will try and make this as simplified as possible in the sense that I don't want to be unfair in talking about data biases in AI and not also being honest about where there are data limitations and biases within the current numerical weather prediction models that we currently use. So I think that's fair to kind of acknowledge that and some of the challenges, and perhaps then at the end maybe the solution is to kind of look at some sort of complementary type approach, certainly at these early stages anyway. So for people that aren't familiar with operational forecasting as it exists at the minute, so obviously it has been in existence for quite some time. So, you know, the initial supercomputers, calculations and stuff going back decades. But the revolution and the progress in terms of the accuracy that we tend to see with numerical weather prediction models is roughly a rate of, we would say, roughly one day of improved accuracy per about a decade of kind of improvements and investments in modeling. So relatively slow in that kind of sense of predictability. It's very computationally expensive, okay, and I'll come on later to how some of the assumptions and the calculations that we need to put into our weather prediction models both make it more expensive, first of all, to run that, but also perhaps allow us to know a little bit more about what is happening that we might not really be able to kind of assess in an AI space. And so I'll come on to whether or not that biases some of the results later. Whereas if we compare that to the rise of kind of machine learning, weather models and AI, you can see that this is just covering, this is a graph from Google research that just covers from January 2019. You can see a vast explosion in terms of the weather models that are being used in this space. And rather than the 1 day per decade, the kind of research here showed that basically 40% over 40 years for our traditional forecasts, which AI has done 90% in 4 years, okay? So this is moving at a vastly accelerating pace, okay? And I think this is why it's important to be aware of those different rates of change when we talk about kind of some of the advancements and so on that have been made. So given that this is obviously a vastly evolving and kind of rapidly growing area of research, so it is an area that we have started to invest in, as have many others in AI at the Met Office. So that sits within our data science framework, and we look at it across the whole organization. So not just within the numerical weather prediction and our forecast modeling, but also for our products and services. So linking back to some of that kind of annotation, post-processing, automated kind of decision support modeling for our customers, and also then through other things that people are using just to help them with their day-to-day lives. But the aspect that I want to focus on is really this AI for numerical weather prediction. And at this point, running it alongside those other tools and resources that we have to kind of assess its effectiveness and where it fits in our kind of forecast process. So we have launched the AI for numerical weather prediction, and basically it's a machine learning tool that we have at both the global and regional level, with the end goal to be able to produce and model both a deterministic, so a one kind of solution, but also an ensemble where we're getting multiple and many different solutions running out in time. And so we've worked with other institutes, recognizing that there are people who can bring the data science to the weather expertise. So we've partnered with both the likes of the Alan Turing Institute, so that's the UK Centre of Excellence for Data Science and AI, but also with academic institutions, so the likes of the University of Exeter through our Joint Centre for Excellence in Environmental Intelligence to look at how we can use that to inform decision making and risk mitigation. And as part of that, we've developed the FastNet model in cooperation with that institute. So this is how we're looking at it. So we're developing that, so machine learning for end-to-end weather forecasting, but as I said, running it alongside those other operational forecasts and forecasts that are being initialized elsewhere to then test how that works in terms of it. But there are some things that we then need to be aware of when we're actually looking at the numerical weather space. And this is where I'd like to talk about some of the data biases then. So I think there are data biases that exist in a number of areas and avenues, okay? So the first one would be, if we look at the image up on the left-hand side of your screen there, so it would be just in the observations themselves. So obviously we're talking about AI as training on these kind of learned realities of the patterns and the weather observations as they see them. We can see from this map that there is a much higher density of weather observations in the Northern Hemisphere versus those across the Southern Hemisphere, not just in the land mass, but also if we look at the kind of ocean content in the Northern Hemisphere versus the Southern Hemisphere, there's a big discrepancy then in terms of our kind of, data point sources associated with that. We also have a difference in the developed and the developing countries, not just because perhaps of the number of observations that they have, but perhaps how long they have had some of those data records for. So where there are shorter records because they have, only evolving observational systems, or they've had limited observational systems in the past, and only now are some of those newer technologies like 3D printing weather stations really coming to the fore, there has been a restriction in those. So where there is a shorter data set range to train upon, then that information that it's learning from is restricted. So the length and quality of those will have an impact too. Even if we take into account remote sensing, that also limits it. So if we look at the areas that they're typically trained to focus on, okay, so they have been, more predominant in different halves of the kind of atmosphere at different times, but it was only really, I guess, in the 70s where we saw an explosion of any of that data really coming into some of these models. And the reason that that's important is because some of the data sets that the AI models are trained on are actually model data sets themselves that I'll come on to in a second. And so in those data sets themselves, where they run from pre-satellite era, we do see a sharp increase in their kind of accuracy post around about 1970. So there is some data biases in that regard. And again, they are more helpful at filling in the gaps in the southern hemisphere. So obviously those statistics across the south are worse than in that kind of pre-satellite era. So there is also other, you can find plots like this that exist. So this is just taken, it's an example of the data biases from the research from Google. And you'll see at the top here that this has climatology versus the Era 5 data. And the reason that I picked this was just to draw some attention to the Era 5 data set that is being used here. So this is an Era 5 data set, a climate reanalysis that goes back to 1940, run by the European Centre for Medium Range Weather Forecasting. And it is still a model data set to a point. So again, because we have those limitations in the resolution and the kind of availability of the observations, it changes. So it collects these sub-daily in situ data satellite points as well as the satellite observations. And we've seen a massive increase. So fewer data being ingested in the earlier years of it. So 17,000 in 1940 up to over 25 million now. So there is some kind of bias within that. And that's linked then as well to some known limitations within that as well. So things like the measurement of the precipitation isn't as good across the tropics or the southern hemisphere as it is across, say, mid-latitudes in the northern hemisphere. So given that this is the data that a lot of this is trained on and then assessed against, that in itself can cause then some bias in that regard. And the other aspect then is the resolution of it. Okay, so some of this is quite coarse resolution. So for this data set, looking at 31 kilometer resolution, and that will then tend to penalize some higher resolution models or models that are trying to look at more point specific. And there is other models which are trying to do that and kind of do the point specific forecast, whereas what these are good at are that kind of synoptic scale and global weather patterns. But it's about knowing those biases and limitations in terms of kind of making our assessment of those parameters. So we can see here, and again, this points out, the kind of, it does show a lot of skill, but I think there's additional skill then in needing to assess where we might know those limitations against. So we can see here that you have plotted in the top corner. So this was a typhoon towards the Philippines in 2018. So in the middle picture, so I think it was TC Yatu, I hope I'm saying that right. But the Pangu weather forecast model correctly and more quickly identified the track of that towards the Philippines, where it took some of the higher resolution forecast models another 2 days to catch up to that idea. But again, the presentation of this, so the original model is against that initial forecast system, whereas the model data is against that reanalysis and hindcast data. So again, is the playing field really the same in terms of where those data biases and assessments are coming from? And then the final thing that I really just want to finish on is this idea of a bias in terms of our interpreting of the AI. So as I said before, with the numerical weather models, we have put into those physical equations. So they are based on what we have learned about the physical properties and parameters of the atmosphere. Okay, so they're based on physical principles, which we're much more comfortable with in terms of trying to distill and understand. Whereas with AI, we have this kind of black box. Okay, so critically, AI isn't really built on this visible principles, okay? And so we have this sort of, I guess, bias in our assessment where we know more about what the numerical weather prediction models are doing, We've learned more about their strengths and weaknesses and limitations, but with the AI, it's this idea of this latent space. So it has these learnt concepts that aren't actually physically represented within the models. So we take precipitation is very strongly influenced by orography, so the topography of the ground. So you'll get increased rainfall on windward slopes, and that's because of the orography. So we try and model that in our NWP, but that's limited because we don't have that at the right resolution. Whereas in the space of AI models, this is a kind of learnt reality from where it sees heavier precipitation. So you can almost assume that it's guessing, there's some process here which is causing an enhancement of rainfall. But again, that's harder for us in our sense to make kind of sense of how it's doing that and how we apply those conceptual models to our assessment then of what's happening within them. And so I think we need to be careful of some of the bias that may come in that aspect from that human-centered side, as well as what's in the modeled output. So I think in terms of this, it's about looking at how do the two modeling approaches kind of come together. And so this is the assessment of the FastNet so far, that we have the critical physical processes that can help us understand what's going on, whereas obviously the AI models are astonishingly fast. So some of these models are 10,000 times faster than traditional NWP. So how do we exploit that then, bearing in mind any of the limitations and also what it's then taking account of as it learns more and more data? And obviously as the data sets become longer, then does that become more robust? Or do we risk it then being trained on other AI data? So that's just some of the thoughts on the data bias. Thank you.
Thank you very much, Helen, for your presentation. Could you please? Yes. Okay, so now we'll give you the definition, which is that biased data occur when the dataset is incomplete, too heavily weighted towards specific attributes, or unrepresentative of all cases. Helen showed that the population bias when she showed that in the northern hemisphere there were more observation, in the southern one less. Also that there is a sample bias, which is exactly what are we talking about. Exclusion bias, when an available variable is deliberately excluded because it's considered irrelevant. Measurement bias, so we have problems in the data, image distortions or other kind of problems, but also observer's bias. So the operator who will give the annotation has its own experience and perspective, and that could bias also the data itself. Okay, so we are at concept 3, and which is model evaluation and transparency. And again, we will ask you to define this concept. So please take back your phones and start typing. So what do you think is meant by model evaluation and transparency?
It's getting more and more difficult here. Anyone daring? There you go. Understanding what you're evaluating.
Don't know.
No secret plans.
That's a start.
Validation.
Okay, and do you think this is important for your work, or absolutely not?
This was quick. This came right away. Okay, we have a little bit of a bias on the screen that is covering the first digit of the yes, but just visually, I think it's a lot, which means it's important. And because we don't have a lot of time and I want to make justice to all the speakers, we quickly move to our next speakers, Dr. Yifang Bang, Professor and Director of the Division of Geoinformatics at KTH Royal Institute of Technology. Dr. Bang, the floor is yours.
Okay, thank you. Good afternoon, everyone. I'm here to tell you about my work related to model evaluation transparency using CASES AI for wildfire detection and monitoring. So here is the outline, but I will skip it, go direct. Why model evaluation and transparency are important? Because model evaluation ensures that AI makes accurate predictions about disasters such as floods, wildfires, landslides, helping better preparedness and timely response, can save lives and reduce damages. And transparency is also important. It ensures and builds trust among stakeholders. For example, emergency responses and decision makers, if they understand how the AI model works, and then they can make maybe better trust the model and then act on the recommendations. So disaster is really high pressure, high stake situation. So it's really important that we have accurate prediction. So inaccurate predictions means false alarms that can cause serious consequences. If you overestimate disasters, then you waste resources to prepare for the disaster. But if you miss the detections, that means you have risks to, properties, human lives, and also environmental damages. And transparency also is very important. It helps the emergency response workers and decision makers really to better understand the prediction in order to act on them with, confidence and trust. So how do we evaluate the models, AI models, the result coming from the models? So there are several parameters, and you see earlier, we also have overall accuracy, kappa, things like that. So here are commonly used. One is called precision, is a fraction of correct positive, really the true positive among the total predicted positives. So true positive and also false positives. So they're not, let's say, not wildfires, but got predicted as wildfires. So that is something you need to think about. And recall is a fraction of true positives among the total existing positive. That means true positive and false negative. That means it's actually fire, but you missed it. So that's false negative. So basically, it measures how well the model catches extra disasters, because you catch some, but you miss them. So F1 score is really the combination, measure the combination of precision and recall. So it's a harmonic metric that is, F1 score is total true positive divided by true positive and combination of false positive and false negative. So then another measure is IOU. It's the intersection over uni. Is like if you have an area and the true positive, let's say those active fires, you detect it, maybe not all of it, and then it includes all true positive, false positive, and false negative. So what are the key elements as transparency? First is the interpretability, the ability to be able to explain how the model arrived at a certain prediction. So you need to explain how you get to this prediction. And this is essential for decision makers to trust the model and take appropriate actions. Another one is accountability, that ensures model decisions can be reviewed and explained, really important aspects. And we also need to consider ethical issues, and transparent models ensure that biases or unfair practices are identified and corrected like, the bias shown by our previous speaker. So this is also very important. So next, I will just show some of our work on wildfire monitoring. As you all know, due to climate change, wildfires have increased in frequency, intensity, and duration across the globe, and cause devastating human, economic, and environmental damages. So since 1972, when many Earth observation satellites that can be used to provide timely and accurate detection and mapping of wildfires. So here are just some examples. To the left is GOES images that you can get these kind of images every 15 minutes. So that helps with detecting fire frequently. On the right are VIRS images, that's twice daily, then you can actually see clearly the active fires. But then that's at 375 meter resolution. But these are more frequent than some other satellites. So we use AI model, it's called a transformer, and we were able to detect active fires continuously on a daily basis. So how do you evaluate this result? So you can't just pick like, okay, a couple of fires to say, oh, I'm 100% accurate. You really need to evaluate this result, maybe across the ecosystems in different regions of the world, in order to evaluate if your results are accurate or not. Two study areas are not enough. So here you can see that, we showed T for fire, that's transformer for fire. Our result compared with a benchmark, it's NASA firm's VIRS active fire result. So then you can see that has improved over the benchmark result. Those are detected using thresholding-based approach. So that's generally the accuracies are higher, F1 scores are higher across board. And also you can see on this side, this column. And also IOU, it's another measure, also higher than the benchmark result. So another AI model I want to show is to map burn areas continuously using VIRS data. The model we use is called Swing Unitor. So they can produce daily burn area maps using VIRS images. So then how do we evaluate our model? So you not just pick one model, just say, okay, this is the model I'm going to use, you get good result. Actually, we evaluate a number of different models. UNet is commonly used, and some variant, and Swing Unit, and then we have the attention unit, Swing Unit. And also you're looking at different parameters, then you look at the F1 score comparison. Our model produced better result, and then better IOU score also across many study areas around the world. And also wildfires, you can map with other satellites that are not affected by cloud and smoke, and that's radar. Our previous speaker have used the Sentinel-1 radar images for flood mapping, and during fires, it can be cloudy and can be also very smoky. So the radar images can also show burned areas, highlight burned areas clearly. So using both optical and radar image, you can see the ones with smoke and clouds, optical and radar without. So using both, we're able to detect burned areas continuously. So we have developed some AI models for this. And how do we evaluate if the models are accurate or not? Yeah. So here, just a quick evaluation, just to show, okay, precision I talked about, and the recall, and F1 score. We also use the overall accuracy and pop-up traditionally. And also, there are many parameters in models. So you also have to look at different parameters to see which one perform better. So, help understanding why you choose certain parameters. So, we also have developed wildfire monitoring application that can monitor fire progression during the fire that can be used. And here the human settlement, how far you're from human settlement, and also with critical infrastructure like power lines, rail lines. And so if you're interested in trying out the wildfire app, and let me know. Thank you very much.
Thank you very much, Yifang, for your presentation. It's great also you created an app. It's going to be extremely useful. Thank you.
Join us here if you like. We go to the Mentimeter. I'm like running fast because time is marching on.
Okay, we are already in the Mentimeter. Thank you. So the definition is that evaluation can be in terms of technical metrics, but of course it depends upon the tasks, and we can use measure of accuracy, but Yifang showed many metrics that you can use to get evaluation scores. But also it can involve trustworthiness of the AI model, so transparency of the data and of the modeling approach, robustness, and explainability. So explainability that you showed also, and also interpretability of the model is extremely important, and it's great that you showed. Okay, so last concept, which is human-centered design and stakeholder inclusion, which is extremely important to keep in mind while developing AI models. Last efforts from you, if you could please write what for you is meant by human-centered design and stakeholder inclusion, it would be very much appreciated. Thank you. So let's see.
Humans first, robots second. Problem solving with the user in mind, indeed. Citizens and co-creators. I think we heard this morning, actually, in the opening speeches, not about me without me, which is exactly readable and usable data. And
of course, if it's important for you and your work in disaster risk reduction or not.
Okay, this is even a clear-cut case of blues against the reds. And while we look at this slide, allow me to go straight to the next speaker. Madhav Apriti, Senior Technical Advisor and Asia Pacific Focal Point at the Red Cross and Red Crescent Climate Center, who is going to give us this presentation. The floor is yours. Thank you.
Thank you. And yeah, just to mention, I don't have a presentation, so it's good. We are already short of time. So hi, everyone. So I think we have enough of a lot of technical things that goes with the AI. So I think it's really important now to bring back the discussion on more on the socio-cultural aspects. And that's when we have this aspects of human-centric design. And what we have normally seen, like with the evolution of artificial intelligence, the technology associated with that, there's a lot of focus is on the data, right? But what we are really missing is like the human aspect to it. It's like how best we like develop those AI technology that can really cater the priorities, the needs, the capabilities as well of the users that it is targeting. And coming from the humanitarian sector, from the Red Cross, I think it's even more relatable, even more important for us, because as we look the application of the AI in the whole risk continuum of the disaster risk reduction and management, the important for the human-centric it's much more, particularly with that, because at the end we are supporting the most vulnerable, we are supporting the affected communities. So that means like whatever technology we are bringing in to support them, I think it has to be like as per their needs, as per their priorities, and they can really understand like how best this AI technology is being developed or is really kind of giving a lot of informations to that. And this is where I think the concept of the human-centric design is really important, because that really puts the users at the center and really kind of try to like design the whole aspects, the AI, the ecosystem around that. And this is, I think, is really important, particularly going back to developing the trust in the AI itself, and which I think Helen was referring. I think that's really a huge issue, because unless we really kind of bring the users at the center, really kind of understand their needs and really make them capable to understand or interpret like what these AI model outputs are kind of informing them, I think we can't really build the trust of the system itself. And also, I think it's important to bring the inclusivity in the whole AI architecture, the AI ecosystem, because like we are kind of, if we are talking about its application in the disaster risk reduction and management, I think we are dealing with a lot of different stakeholders. And this is where I think we are currently seeing quite a bit of gap, because we have the AI researchers, AI scientists, and we have the practitioners, the DRR people, and there is a huge disconnect. I think the language they are kind of using, because the AI people, I think they are more on the data, more on the metrics, whereas the practitioners, the DRR, the humanitarian people, I think they really want to know whether whatever they are producing is really like helping them or not. They just want some sort of like successful case, right? So it's important like how we bring these two different domains together and really come up with some sort of the terminology as such, right? That can really be relatable both with the AI domain and also with the kind of the users that it is targeting, which we are talking about the disaster risk reduction and management. So yeah, there's a huge potential, huge opportunities of the artificial intelligence, particularly with regard to like specifically I can refer to the early warning, early actions, the forecasting, which I think Helen was mentioning, the kind of improvement that we have seen with the AI models, with the forecasting certainly gives us huge opportunities. But at the same time, I do see like there is a huge opportunities on the overall risk analysis, mapping. I think we saw with the fraud extent mapping as such, really going down at the much household level, at the granular level. And this is where the AI really kind of opens up that possibilities to really know, okay, which are these communities which have these kind of the risk. And the risk is changing, it's dynamic. And this is where I think this complex AI model can really start to learn. But at the end, I think for any AI model to run, to have a good reliability on its model outputs, the data is important. Like what kind of data that we are bringing in, what kind of how these data, like they are being trained. And this is also kind of the issue I see as challenges in the AI itself, because like, for example, as a humanitarian, like we work in a lot of those regions where there is huge data is scarce. Right? We don't have the data we do not know like what are the risks that underlies. So obviously we want to have the AI to really fill those gaps, but at the same time we also see the limitation because we don't have the data, because the AI needs data to be trained to really kind of give that the reliable model outputs. And this is where I think the collaboration is really important, right? How we like bring these different people, the users, the AI practitioners, the AI researchers all together, and really kind of start with like what are these, like there are existing data sets itself which might not be really relevant for like with the AI that can really go as a direct output input, but as collaboratively we can like develop a data set itself, right? We can really have this AI to first develop the data sets, and then I think then we can start like coming up with some of these the model output that can really help to inform us more on the early actions or in the broader disaster risk management. This is where I think we have started to explore a bit of the potential, particularly on the risk mapping, the impact analysis, particularly on the anticipated actions. We do see, I think there is a lot of potential in that, because that is where we are like seeing a huge gap, not only in the forecasting part, but also on the more on the risk mapping, impact analysis kind of thing. And this is where we can definitely leverage more with the AI technology. But just to conclude, what I can say is, yes, there is a lot of opportunities, there's a lot of hype with the AI, but at the same time, I think it's also important for us to be vocal enough to communicate what are its limitations. Like what are like like the biases. I think we talk about there are the biases, like how it can be misleading, particularly when it comes to decision making. So it's important like to have this clear communication across the stakeholders whom we are talking, the users whom we are targeting. So that's, I think it is really important. So yes, let's leverage the potential of AI in the DRR and the disaster instruction and management. But yes, without exaggerating it. I think that's really important. So I would like to stop here. Thank you.
Thank you so much, Madhav. And before we go to our closing remarks, I think we have the last two slides.
Yes, I give you quickly the definition that we came out with, and then we can move. So the human-centered design means clearly identifying and working with the target user, as Madhav said. So that it's possible to integrate them in the development of the AI-based communication tool and to ensure that the final product meets their needs. So this is our definition. And
key takeaways. So keep going. What lessons will you take from this session, from today's session? Open responses. Okay.
Anonymous again.
The black box will grow bigger. Yes, AI is a useful tool, but still needs human intervention and assessment. It must be integrated in DRR, should be people-centered, is powerful but limited and needs a human touch or brain. A lot of opportunities in DRR, but we need to be mindful of how to apply AI. Responsible and effective AI use. Thank you. Thank you.
Thank you.
And what could we do to help you to better understand and apply AI in your DRR work? That's really important. We're going to take these answers and study them. They are anonymous, but please do let us know. You know, a center like APDIM, the one I run, that works in partially in this field, it's important to us to get a sense. Show the QR code again, okay? Training, got the message.
It's not anonymous, we lie. No, no, it's a joke.
No, but I see the word training coming up 3-4 times in different ways. Better data model, better, more transparency, open data source, that is a huge question that keeps coming up. Investment for less developed countries. So thank you, really interesting insight. And I think now we are ready for our closing remarks, and I'm really pleased to invite to the floor the former special representative of the Secretary General for Disaster Risk Reduction, Margareta Wallström. Please join us. I should say Margareta has been really, for the few people that may not know of her, yes, I will take the last 10 minutes. She's really been instrumental in moving the DRR agenda where it is now, the brain and the engine behind the Sendai framework and behind this kind of multi-stakeholder collaborative approach. And so it's really with great pleasure that I give you the floor.
Thank you, and a really interesting event, I must say. Instead of preparing my words, I got stuck with your maps and the wildfires mapping, everything that we wanted to use. But actually, I will just give you an anecdote. When I became the then SRSG, 20 years ago, almost, no, 15 years ago, I met with the then existing science group of UNDRR, most of them seismologists. So I said, really nice, valuable, and they looked at me and said, what do you want us to do? So I said, well, I thought you were going to tell me what to do. So that was the start of a wonderful cooperation, of course, but it also said something about the continued gap. I have spent many, many hours at universities with very talented people, and the question that comes up very often is, why don't they listen to us, the decision makers? So I said, well, personally, my recommendation to you is, because there were ideas of we need people who interpret our science and our knowledge, and I'm not sure we can afford yet another class of people helping us to understand the reality. So I said, can I give you an advice? First, you tell me what you know that you think is relevant for me. And then if I ask you, you tell me how you reach that conclusion. Just to say, you know, when I put myself in the role of being a decision maker, apart from the obvious age gap, there is a generation gap or 2 generations. Many of you probably filter in most of what you see here of the technical and the science background. I just look at what's useful for me. And that's because I know the area. But if I'm a decision maker, and now I look really at the reality that I deal with a lot right in my nowadays, is municipal level, hugely overworked people, no money, certainly no experts at local level, and they are under pressure time-wise and financially. And they are told to do a plan for your climate adaptation, do a plan for your DRR from the top. Yeah, sure, they say, and then they get on with their life, and then the next flooding happens. So really, I think the big challenge of the opportunities, the scope of knowledge we have access to, and just to understand that Google doesn't always help, which you show us the very good example of what happens when you Google, is to actually take this next step of, I wouldn't say training, because I think a lot of people actually understand a lot, but develop the practice of asking questions to the knowledge that exists. Train yourself, us, to ask pertinent questions. We cannot just be receivers and consumers of expert knowledge. That's my message. Thank you.
Thank you so much. Thank you so much. Maybe Dr. Marciano, would you like to join us just to take a photo op with the panelists? And then we'll clear the room. We are done. We're just taking the final photos. Thank you so much, everyone, for being here. It's been a pleasure.
Thank you.
Thank you.
Thanks.